Hey everyone, welcome back to the channel. Today we are talking about data consistency models in distributed systems, specifically about strong consistency and eventual consistency. Whether you are building a critical banking app or a large-scale social network, understanding these models is crucial. So let's dive in. First, let me delete everything here first, so we can start. Um, First, let's start with what is strong consistency. Let me. Yup. I guess it's good on the machine on the screen now. Okay, so strong consistency means that once a write operation is acknowledged, all sequent reads will reflect that most recent write. In other words, your system behaves as if there is only one copy of the data everyone sees the same state instantly. So also, if you wanna talk about it simpler, we can say that strong consistency means that all nodes will read the same thing at the same time and they will get the same result. The pros and cons of this one. The pros is that it's a pretty predictable, like read behavior, like no stale data at all. Number two, it's easier mental model for application developers. What are the cons? First, there is higher latency, and we could talk about why specifically strong consistency have higher latency. Because coordinating across nodes can be quite slow. Number two, reduced availability. Like if one node is down, you might have to wait until it's back to guarantee consistency. Okay, let's talk about eventual consistency. And first, let's talk about what is exactly eventual consistency. Let me just take the text and put it here. Okay, so eventual consistency ensures that given enough time to all nodes in the system, given enough time, all nodes in the system will converge to the same value, but it doesn't guarantee when. If you read data immediately after a write, you might get older data on some nodes. So basically, I would say eventual consistency means that not all nodes will read the same thing in the same time, specifically after a write request. Yeah, this is how we can think about it. The pros and cons of this one: first, high availability because nodes they can accept reads and write even if others are offline. Number two, low latency because no need to coordinate with every node for each write. The cons of this one, we have inconsistent read because some nodes may lag behind. Number two, we have complex error handling, like if your application needs strict ordering or up-to-date data. Okay, we need to talk about the use cases, like when to use eventual consistency and when to use um, yeah, I guess, and when to use a strong consistency. Let's start with the eventual consistency. You can use eventual consistency in social networks, caching layers, or large-scale distributed surfaces where it's okay for data to be slightly out of dated. Example for that, let's say that for example, like there is a user who let's say that user one or user A like on a social media post an eventual sync to all replicas. Or a brief delay is acceptable. Like maybe one user can say like, see, there is 4,000 like, but in the other word they are maybe like 3,000. Maybe they are 4,001. So yeah, it's not that consistent. So there is one like missing, but it's not the end of the world. Um, let's talk about the strong consistency as well. When to use it? Use strong consistency in banking, financial transactions, inventory updates, or critical systems where stale data or stale reads are unacceptable. An example for that, let's say that user A um, has a bank account and he wants to see the balance, and the balance must reflect every debit and credit in real time. Okay, let's talk about the trade-offs and cap theorem. If you don't know what cap theorem is, I created multiple videos talks about cap theorem, so that just like check them. Yeah. So in terms of the trade-offs in the cap theorem states you can only pick one of two: consistency, availability, and partition tolerance. In distributed system with a strong consistency, you often sacrifice availability under network partitions to maintain data consistency. With eventual consistency, you aim for high availability and can handle partitions, but you sacrifice immediate consistency. Choosing a model depends on your application's tolerance for inconsistency versus the need for real-time accuracy. Okay, we can talk about best practices, and I guess we will just go to our conclusion. Okay, the first thing you need to identify the requirements. Like if your use case demands absolute correct data, like financial apps, strong consistency is a must. If you can tolerate stale reads, like social media feeds, for example, eventual consistency is okay. Number two, hybrid approaches. Like many systems use a mix, like some data is strong consistent, others eventual consistent. Number three, graceful handling. If using eventual consistency, ensure your app handle conflicts and merges data gracefully. Yeah. So ultimately, no model is better across the board. It doesn't work like that. It's about meeting specific applications and user experience needs. Okay, let's go to our conclusion, and I guess we will end the video there. Yeah, that's a strong consistency versus eventual consistency in a nutshell. Strong consistency offers immediate, accurate views but can hurt availability and latency. Eventual consistency is highly available and fast but allows brief periods of inconsistency. Knowing which to use or how to combine them is key to designing robust, scalable systems. If this helped, please like, subscribe, and let me know about your experiences with consistency in the comment section below. Until next time, keep your data consistent or eventual consistent, like whatever you prefer.